طيب okay شباب السلام عليكم. إن شاء الله today we will start chapter 4, the application of the first law of thermodynamics for a closed system, or what we call actually energy analysis of closed system. As I told you earlier, in chapter 2 we have developed the equation for the first law of thermodynamics for closed system, and also the equation for the case of a steady flow open system. And we said we'll have more application inshallah in chapter 4 and chapter 5 after learning how to calculate the properties of pure substance. We have learned in chapter 3 how to calculate the properties if the working fluid is a steam. Then we can use the steam table. If the working fluid is the refrigerant, then in this case I will be using the refrigeration table to calculate all the properties, including specific volume, internal energy, enthalpy, and also the entropy at any given point. Also talk about the ideal gas. In case when we have gas, we can apply the ideal gas equation of state, even the ideal gas equation or the modified equation using the compressibility factor Z. Then now we can move actually to chapter 4. Then we can apply the first law of thermodynamics, and now we are able actually to calculate all the properties of a system at a given state. Then we can have some examples. Then we can apply the first law equation to calculate the heat transfer or the work out of a system. طيب, this is inshallah will be our subject. This chapter 4 will not have many new equation. Just will consider the equations that we have developed in chapter 2, which is Q minus work. Simply Q minus work is equal to the change of energy of the system. Here's the objective of this chapter. Inshallah, we'll examine first of all, we talk about different kind of work, including electrical work. We have considered also the spring work, shaft work, and different kind actually of work. What is missing actually is what we call the boundary work, which is the work exerted by the system, either on the system or by the system, when we have one of the boundaries is moving. And this work actually for a closed is only applied for the case of a closed system. Because in the case of open system, it is actually defined as control volume. The volume is constant. So in this case, we don't have moving boundary in case of open system. So only the boundary work is applied for the case of closed system when we have one boundary of the system is moving. And the most common application for this case when we have a gas or fluid inside a piston cylinder device. So in this case, if the piston is moving up or down, then in this case, it can create what we call actually the boundary work. The work in general for a closed system is integration of PDV. We have proved this relation in chapter 2, and we will talk about it again today, inshallah. That's why this boundary work is called as actually as the PDV work. Inshallah, we'll talk about this work, how to calculate the boundary work when we have one of the boundaries is moving. Then inshallah, we'll identify the first law of thermodynamics. As we said, most of the material in the middle of this chapter are just repeated from chapter 2. We talk about the first law of thermodynamics. We said it is the same as conservation, based on the conservation of energy principle. Energy cannot be created or destroyed. Based on this concept, actually, we said for any thermodynamic system, energy input minus energy output will equal to the change of energy of the system. And based on this relation, we have developed the first law equation for closed system, which is actually we have developed already this relation in chapter 2, which is Q minus work is equal to delta U. So inshallah, we'll have some application in this chapter, and we'll try inshallah to solve some problem and see how we can calculate the heat transfer or the work out of a system. Inshallah, in this chapter also, we'll talk actually about the specific heat at constant volume and the specific heat at constant pressure, and we'll learn actually how to relate both of them actually to calculate the change of internal energy and the change of enthalpy. We said last time actually in very brief way that delta U is equal to CV multiplied by delta T, and delta H, the change of enthalpy, is equal to CV delta T. Inshallah, we'll learn in this chapter how to calculate delta U and delta H based on actually in relation to the values of a specific heat at constant volume and the specific heat at constant pressure. So this is the whole about this chapter. It will be just simple. We don't have more equation, just the equation we have developed, and inshallah in this chapter we'll just have more application. Before we move, as I told you, we consider the different kind of work. But what we are left with actually is the boundary work. Boundary work actually is the work when we have one of the boundaries is moving over the system. And this kind of work actually is only applied for the case of closed system, because open system is a fixed volume. It is defined as control volume. So the volume of the system is fixed, so we don't have any movement of the boundary in case of open system. Type, let's consider the boundary work for a closed system, how we can calculate actually the boundary work. Okay. As we said, boundary work is the work actually exerted either on the system or by the system when we have one of the boundaries actually is moving. And the most common example for this, when we have a fluid, let's say we have gas or something, this gas actually is at a given pressure inside the piston cylinder device. So if we heat up actually, let's say we added heat to this gas, and this piston actually is allowed to move, then in this case actually this pressure will start to raise within the system. And this pressure will apply actually a pressure force. This pressure force actually normal and to inside actually of this piston. Okay, so this is the direction of this pressure force. It will equal to the pressure multiplied by this area. The area, the cross-sectional area of this piston. And due to actually this increase in pressure, this piston actually can move a distance, let's say delta S. So as we have force, applied force, pressure force, and we have movement, then in this case we have work. This work actually is called the boundary work because it is the work associated with the movement of the boundary. This work is equal to, we call it actually delta boundary work, because here we assume we have a small amount of heat added. So we have actually a small pressure rise and we have a small distance movement delta S. So delta boundary work will equal to the force multiplied by the distance delta S. I think we have done this. Force is equal to pressure by area, and this is multiplied by delta S. Area, cross-sectional area, multiplied by the distance delta S. We call this actually as the change of volume delta V. Then we can say delta boundary work will equal to B equal to pressure multiplied by the change of volume delta V. To calculate the total work, the boundary work, then in this case we have to integrate, in this case, integration of BdV from V1 up to, from V1 to V2. Or we can just write it here, the boundary work is equal to integration of BdV. And that's why we call the boundary work as the BdV work, because it is equal to integration of BdV. Okay? So can we represent this process on, let's say, on the pressure specific volume diagram? This process actually, let's say we do have any system undergo actually any process, just in general process from state 1 up to state 2. If you look at the area under the curve, we said the area under the curve on the PV diagram is equal to representing the work done by the system, either the work done by the system or the work applied by this system. And I think we have proved this earlier. We can just take here an element. This is actually a rectangular element. Its width is delta V and its height is B. Then in this case, delta area will equal to just the width multiplied by the height. It will equal to pressure multiplied by delta V. And then if we need to calculate the whole area under this curve, we can just integrate this delta area to calculate the whole area under the curve. It will equal to integration of BdV. And also the boundary work is BdV, integration of BdV. That means the area under the curve on the PV diagram represent actually the work done, which we call it in this case actually as the boundary work. Okay? Type boundary work, this work is mainly function of delta V. This work can either be actually expansion when we have the increase in specific volume from state 1 up to state 2. Then in this case, delta V is positive. So this value, delta V, if it is actually positive, then we have, in this case, we have expansion. So in this case, the piston will be expanding, the gases will be expanding, it will be moving out. And delta V is positive, and in this case, the work actually is, we call it expansion work, and its sign in this case is positive. Okay? Type, if we have compression, if this process is just reversed from state 2 to state 1, then in this case, actually, delta V will be negative in this case, and the process in this case actually is just a compression process. And in this case, this work, we call it actually a compression work, and it should have actually a negative value in this case. So either the boundary work can be either applied by the system. So in this case, the sign of the work is applied by the system. We have expansion work. So the sign of this work in this case will be positive. The equation itself will just give me this sign. It will have a positive value expansion. Or if the reverse, if the system actually is losing heat is rejected, then in this case, the piston will be moving down in this case. So the system will be contracting. So the volume will be reduced. That means actually this work is applied on the system. Or we can just press this piston down there, then we apply work on this system. So the volume will be reduced, and the work in this case, the boundary work in this case, will have a negative sign. Okay. But if we have a system, let's say working on a cycle. Working on a cycle, that means we may have expansion work and we may have also compression work in this case. But if the system is working on a cycle, so we can represent this process also on the pressure specific volume diagram. Let's say simply the cycle is just two processes. One process is expansion from state 1 up to state 2, and we have another compression process from state 2 to state 1 in this case. Okay, but the work actually, the expansion work from state 1 up to state 2 is just the area under the curve. And this sign actually is this expansion work, and its sign is positive. But this work from 2 to 1, this is actually a compression work, and its sign actually should be negative in this case. And in this case, the work net for the cycle is just equal to the expansion work minus the compression work. Type this is actually, let's say this is the compression process, and the red is the expansion process. The work for the expansion is the area under the curve. This is the area. And the work for the compression is just this area, and it is negative sign. So negative will go with the positive. Then in this case, this area here, between actually the two curves, this area actually represents the work net, the net work of this cycle, which is the difference between the expansion work minus the compression work. So if we have a cycle, so for a cycle, for system working on a cycle, the net work will just equal to the expansion work minus the compression work, and it represented actually on the PV diagram by the area contained by the two curves, the area between the two curves, which is actually this area. Okay, the area between the two curves is just representing actually the net work. An example actually of a system working on a cycle, and its work is equal to the expansion work minus the compression work, is the gas turbine. We said I think you know about actually the hydraulic turbine. When we have water at high level is coming actually and hits the blade of the turbine, then it can generate work. We have another kind of turbine which we call actually the gas turbine. In the gas turbine actually consists of compressor. This compressor actually is connected to the shaft with a turbine, and in between actually we have a combustion chamber. Okay, this combustion chamber, it takes the air coming from the compressor. So atmospheric air is coming to the compressor at atmospheric pressure. So its pressure is raised here inside the compressor, and actually this is high pressure. So the density in this case will equal to pressure divided by RT. Pressure is high, that means we have high density of the flow. High density of the flow, that means actually we have higher mass flow rate. Mass flow rate is density by area by velocity. High density mean actually we have higher flow rate. So we use the compressor to compress the air at higher pressure. Then first of all, it compresses the air to the pressure of the combustion chamber, and the compressing air will raise actually its density, and it will raise also the mass flow rate of the air. Then for this combustion chamber, raising the mass flow rate of air, we can actually give more mass flow rate of fuel, M. fuel, then we can burn the air with the fuel in the combustion chamber. At the exit of this combustion chamber, we will have exhaust gases at high pressure and high temperature, or high enthalpy. High pressure, high temperature, so we have gases under high enthalpy in this case. Then we can pass them through the turbine. The turbine is fixed blade, and moving blade, fixed blade which is the nozzle actually, and we have moving blade having buckets, then actually this enthalpy or high flow energy would be just converted to kinetic energy, and this kinetic energy of the hot gases will hit the bucket. Then in this case we can generate actually shaft power out of this turbine. So the shaft of this turbine will be moving in this case, and we will generate shaft power. Type to drive this compressor actually its function is the reverse of the turbine. It takes the air at low pressure and it raises the pressure. So it increases actually the flow energy of the air. But actually in comparison to this one, it has to consume actually shaft power. So we have work input to the compressor in this case. So that's why we connect the compressor to the turbine at the same shaft. So part of the shaft power output of this turbine will be just actually used to run this compressor. Okay. And in this case, actually, the network, this system actually is working on a cycle. This is the exhaust. Again, we'll take another amount of air, we'll burn this air with the fuel, generate hot gases, then we expand this hot gases inside the turbine, and then we just move the exhaust outside of the system. And then we can repeat the cycle. This gas turbine is used in the electrical power plant, and Saudi Arabia actually is the world top gas turbine user. It is actually the world top gas turbine user in the world. We have actually the greatest number of gas turbines in the world that are existing here actually in Saudi Arabia for electrical power generation. So usually we connect this shaft of this gas turbine with an electric generator, then we can generate electrical power in this case. Okay. But for this cycle, this gas turbine to generate actually continuous shaft work, it has to work on a cycle. We have to repeat this process. And in this case, the net work of this cycle will equal to the work of the turbine minus the work of the compressor in this case. And this cycle can just be represented on the PV diagram by this curve. And there is actually a drawback of the gas turbine in comparison to steam turbine. The drawback here of the gas turbine is that actually part of the shaft work generated by the turbine is consumed actually to run the compressor. Okay, which is unlike the case of a steam turbine. In the case of a steam turbine, we just burn the fuel in a boiler, then actually we use the heat of burning the fuel to heat up the water to convert it to steam under high pressure, high temperature. Then we pass this steam inside the turbine. Okay, in this case we don't have compressor in this case because first of all we have to have high pressure. But in case of steam, we have liquid water at atmospheric pressure. We use pump, and the pump actually, the power required to drive the pump in case of a steam turbine or a steam power plant is much low. Actually, the power required to run the compressor, because compressor is dealing with gas, pump is dealing with liquid. So in this case, actually, to compress the gas, you will need actually much extra power, because actually the higher specific volume of the gas as compared to the case of liquid. So one drawback of the gas turbine is that part of the produced power of the turbine is used actually to run the compressor. This is actually in comparison to the steam turbine, which does not require actually to have a compressor. Because in this case, we have the working fluid is zero water first, and we use pump with low input power to run, to raise the pressure of water up to the boiler pressure. So let's see how we can calculate the boundary work. We said boundary work is integration of BBV. And this boundary work is mainly function of pressure, the variation of pressure as function of the volume. So let's see some special cases and how we can calculate actually in each of those cases, how we can calculate the boundary work. So let's consider some special cases for the calculation of the boundary work. The first case actually, when we have isochoric process. Isochoric process. Isochoric means the volume is what? The volume is constant in this case. Like when we have actually, when he said we have rigid tank, or let's say we have rigid vessel, okay, or closed rigid container or something like this. All of this actually means the volume is constant in this case. So volume is constant, that means delta V is equal to 0. We don't have a change of volume. Just we have a rigid container or rigid volume in this case. So we don't have movement of the boundary. And in this case, when we apply the boundary work, it will equal to just the integration of BBV volume is constant, that means delta V will equal to 0. And in this case, we don't have boundary work, as actually we don't have moving boundary in this case. Okay. Let's consider another special case when we have isobaric process. Isobaric process, which means actually the pressure is constant in this case. So first of all, let's represent the isochoric process on the PV diagram. Isochoric, that means the volume is constant, system is closed. So that means actually the specific volume, which is the total volume over mass, will be constant in this case. So we can represent on the PV diagram by just vertical line, either from state 1 to 2, or actually from state 2 to 1. But for isobaric process, in this case, when we have a gas, let's say we have a gas in a piston cylinder device, okay, and we just added heat actually to this gas, then this gas will expand. In case when we have free movement of the piston free movement, or we have actually, if we said actually we have a frictionless piston. Frictionless piston, that means actually this piston is moving freely in this case. So as we add heat, so this piston will have the freedom to move. Then in this case, actually, when we add heat, the gas will try to expand and it will be able to expand. And that's why in this case, the pressure inside this piston cylinder device in this case will be remaining constant in this case. Type how we can calculate the boundary work in this case. So the boundary work is equal to integration of PV. We said pressure is constant, then we can take it outside. So it will equal to the pressure multiplied by integration of dV. So it will equal to V2 minus total volume V2 minus V1. Or it is equal to actually the pressure, total pressure, the pressure multiplied by mass. We can take mass common. This is a closed system, so mass is constant. So pressure multiplied by mass multiplied by the specific volume in this case. This total volume is equal to the specific volume multiplied by mass. So it will equal to pressure multiplied by mass multiplied by specific volume V2 minus the specific volume V1. Okay, and this is actually the boundary work in case when we have an isobaric process. He may tell you in the exam or something or any problem, this is actually a piston-free movement, or we have frictionless piston not connected to any device. So that means in this case the pressure is constant in this case. But when it comes to substitute, then in this case, if this pressure actually is calculated in kilopascal, because we'll take this value of the boundary work and we'll apply later on, inshallah, the first law equation, Q minus work equal to delta U. And we have to consider actually this work substituted in the equation in kilojoule. So for this one to be in kilojoules, the pressure in this case should be in kilopascal, mass is in kilogram, and specific volume is in meter cube per kilogram. And this is actually the second special process when we have an isobaric process. We have a gas in a piston cylinder device undergo actually an isobaric process. And this process can just be represented actually on the PV diagram or the TV diagram. In this case, actually just a horizontal line, either from state 1 to state 2 or from state 2 to state 1 in this case. Okay. So let's move actually to the third special case, when we have actually polytropic process, what we call actually polytropic process. Polytropic process is a process actually in which the pressure is varying with the volume based on the relation actually BV to the power n is equal to BV to the power n is constant. And n is called actually as the polytropic index. So n is just given as the polytropic index of this process. We can represent actually this process also in the PV diagram. Can be represented actually by this curve. Either this process actually is an expansion process from state 1 up to state 2, or it could be actually a compression process from state 2 up to state 1. And the relation between pressure and volume in this case is BV to the power n is constant in this case. And the n is just actually an index. Usually it is greater than 1. We call it actually as a polytropic index for this relation. Type as BV to the power n is constant, that means actually BV to the power n is constant at any point here from state 1 up to the final state, state number 2. Okay? Or based on this relation, we can just say BV to the power n is constant. Then in this case, we can say the pressure will equal to V to the power minus n multiplied by the constant C in this case. And based on this relation also, we can apply this relation at state number 1. Then we can say V1 to the power n. This also will be constant at any point from state 1 to state 2. So it is equal to V2 to the power n. And this is actually also constant at any point. At any point here from state 1 to state 2, we can say actually V1 to the power n is the same as Bx multiplied by Vx at any point to the power n is the same as V2 to the power n in this case. And this is the value of the constant can be represented at any point. But let's get back to this relation. Based on Bv to the power n is constant, then the pressure will equal to V to the power minus n multiplied by the constant C. And then just apply the boundary work equation, which is equal to integration of V dV. Pressure in this case is integration of V to the power minus n multiplied by the constant C. Integration actually of this is C to the power V minus n is just as a V. Okay, integration of B dV. This integration actually from volume V1 up to volume V2 in this case. So let's do this integration. Then it will be integration. Constant, we can take it outside. And the V to the power minus n, integration of V to the power minus n, it will be V. This is equal to the constant. We can take it outside. And this integration will equal to V to the power minus n plus 1 divided actually by 1 minus 1 plus n. And this integration is done from volume V1 up to volume V2. Or it will equal to V2 to the power minus n plus 1 minus V1 to the power minus n plus 1 divided by minus n plus 1. And outside here, we have the constant C. Okay? So let's take this constant C as equal to actually V1 to the power n and multiply it actually by this term V1 to the power n. And let's take this constant as V2 to the power n and multiply this constant here as V2 to the power n. Okay? So let's look at this term. It will be V2 multiplied by V2 to the power minus n plus 1 multiplied by V2 to the power n. So in this case, it will be just equal to V2 to the power 1, as actually minus n will go with plus n in this case. Unlike this, actually, the other term. Then we can get this relation for a polytropic process. We can just calculate actually the boundary work. So in this case, the boundary work will equal to B2 multiplied by V2 minus V1 multiplied by V1 divided by minus n plus 1 or 1 minus n in this case. Okay, this is V2 is the total volume, which is equal to actually the mass multiplied by specific volume. So we can write it as actually mass multiplied by the pressure V2 multiplied by specific volume V2 minus B1 multiplied by specific volume V1 divided by 1 minus n in this case. And this relation actually, we can calculate using this relation. Actually, if we have a gas in a piston cylinder device undergo a polytropic process, then in this case we have boundary work. This boundary work is calculated based on this equation, B2 multiplied by total volume V2 minus V1 divided by 1 minus n. We can take M as constant because this is actually a closed system. Mass is constant at state 2, same as state 1. Then we can take it as common. Then it will be pressure multiplied by specific volume in this case. B2 V2 minus B1 divided by 1 minus n. But in case when we have ideal gas, In case when we have an ideal gas, we have in this case BV, pressure multiplied by specific volume, is equal to the gas constant R multiplied by the temperature T in this case. So in this case, we can just remove BV and we can represent by RT. So in this case, the boundary work for the case of ideal gas will equal to MR multiplied by T2 minus T1 divided by 1 minus N in this case. So if the working fluid, we have an ideal gas inside a piston cylinder device. If this gas actually is an ideal gas, then actually this equation can be applied, or we can use actually for ideal gas, we have BV is equal to RT. Then in this case, we can just apply here, then the boundary work will equal to mass multiplied by R multiplied by T2 minus T1 divided by 1 minus N. N, as I told you, is the polytropic index in this case. Okay. This work can be either positive or negative. Positive if it is expansion from 1 to 2, and it can be negative if the process actually is a compression process. So he will tell you for any application about the pressure relation, pressure with volume, when we have actually any working fluid in a piston cylinder device with the movement of the piston, then we have boundary work, and we have to calculate this boundary work through the integration of BdV. Okay. We are considering here some special cases. We have considered isoporic, the boundary work is 0. We have considered the case of isobaric, pressure is constant, then we calculate the boundary work through the integration of BdV. And when we have a polytropic process, then in this case also we can calculate boundary work through integration. It can be in a relation. It may give you actually pressure, any pressure as function actually of the volume V. Then in this case, just I will take this relation and I will say boundary work is just equal to integration of BdV from volume V1 up to volume V2. Okay? But we are just here considering some special cases based on which actually we can get a relation for the boundary work. So the last special case number 4, when we have isothermal process. Okay? So we have a gas in a piston cylinder device undergo actually an isothermal process. Isothermal process, in this case the temperature is constant. Actually the isothermal process is a specific case or a special case of the polytropic process. When we have the polytropic index is N is equal to 1, then in this case we have an isothermal process in which actually pressure multiplied by the volume in this case is constant. So BV is constant in this case. Okay? You can look at it easily. If we have an ideal gas, we have BV is equal to RT. If the temperature is constant and R is constant, that means actually pressure by volume is constant in this case. Okay? So the isothermal process is a special case of the polytropic process under which actually the polytropic index N is equal to 1. And in this case, we have BV is equal to constant in this case. And it has very similar representation for the process actually on the BV diagram, very similar to the polytropic process. It could be expansion and also compression. So if we apply this relation, so we can say B1, V1, as it is constant at any point, so it will be the same as B2, V2, and this is actually is equal to the constant C. But based on this relation, we can say in general the pressure will equal to the constant C multiplied by the volume to the power minus 1. Okay, and in this case we can calculate the boundary work integration of BdV that will equal to integration of B, which is C multiplied by V to the power minus 1 dV, or delta V over V. This integration from V1 up to V2. Integration, this constant, we can take it out, and the integration of delta V over V, which is then V2 over V1. So this will equal to a constant multiplied by ln V2 divided by V1. And this constant is equal to BV, either B1, V1, or B2, or B2, V2. So that should equal to, this one should equal to B1, V1, ln V2 over V1. Or it is the same as V2, V2, ln V2 over V1. But V2 over V1 from this relationship, V2 over V1 will equal to what? B1 divided by what? B1 divided by B2. So this relation, we can just replace V2 over V1, ln V2 over V1. It can be actually B1 over B2. Okay, so if the pressure is given B1 and B2, then in this case we can apply this relation B2, V2 or B1, V1, ln B1 over B2. If the specific volume, the total volume is given V2 and V1, or a specific volume, because the mass is constant, we'll just divide. Then in this case, if the specific volume or volume is given, then we can use this relation B1, V1, ln V2 over V1. And in case of ideal gas, when we have an ideal gas, this BV is equal to MRT, and in this case, the boundary work, we can also have this relation MR BV, B1, V1 is MR T1, or B2, V2, MR T2, but T1 is the same as T2, temperature is constant, so it will equal to MRT multiplied by ln V2 over V1, or MRT ln B1 over B2. And by this, actually, we can calculate the boundary work when we have an isothermal process. Okay? Let's look here, see some examples. This is what we said. But the proof itself is not there. So I think you have to look at this one. Here is an example. The first example, we have a rigid tank. So do we need to continue reading this problem? It is a rigid tank. So do we have boundary work? Rigid, the volume is constant. So in this case, boundary work is integration of B dV. Then delta V is 0. Then in this example, actually, the boundary work will equal to 0. So in case when we have a rigid tank, rigid container, rigid vessel, all of this actually means we don't have movement. We don't have movement of the boundary, and in this case, the boundary work will equal to 0. Okay. So this example we don't need actually to go through, and the representation of the process in this case is just as vertical line because the volume is constant in this case. Okay, he said we have air in this tank and give B1 T1 and B2 T2, and we need to calculate the boundary work. As it is a rigid container, so the volume is constant, so the boundary work will equal to 0. Okay. So for this process here, he said we have a frictionless piston device, piston cylinder device. Frictionless, as we said, and it is connected. It is not connected actually to a shaft. So we have a frictionless piston cylinder device that contains water. Contains actually a mass of 5 kilograms of water. He said this is actually a frictionless piston. So that means in this case actually, and this piston is not connected to a shaft. That means in this case the pressure within the system, if we added heat in this case, and this is what he said in this process, we just added heat to this water in this case. That means while the heating process, in this case the pressure will be constant, because the pressure B1 will be the same as B2. He said the mass of this water, he said steam, 5 kilograms of steam existing at 400 kilopascal, so the pressure B1 is 400 kilopascal, and temperature T1 is equal to 200 degrees. He said actually heat is now transferred to the steam until actually its temperature reach temperature T2 equal to 250 degrees. Okay. He said this is a frictionless piston. If this piston is not attached to a shaft, and actually its mass is constant, so it is not connected to a shaft or anything that actually may become as an obstacle actually for its movement. So it's just free to move. That means in this case the pressure B2 will be the same as B1, which is equal to 400 kilopascal. Okay, and we need to determine actually the work done by steam during this process. So if we have a gas in a piston cylinder device and we added heat and the piston is moving, then in this case what kind of work do we have in this case? So in this case, as we have movement of the boundaries, then we have boundary work in this case? Do we have electrical work? We have electric heating coil or something? No. Do we have shaft work? We have paddle wheel or something inside this tank? No, we don't have. So the only kind of work we do have in this case is the work due to the movement of the boundary in this case. And we have the boundary work is equal to integration of BdV. We said in case of isobaric process, that should equal to the pressure, can take it outside as constant, multiplied by V2 minus V1, or pressure multiplied by mass multiplied by specific volume V2 minus specific volume V1. Like he said, as I told you, for any problem, I have to decide first either the system is closed or open. So this is a gas and a piston cylinder device, so the system is closed. So in this case, I will apply the first law for a closed system. The second, that we have to determine actually in this case the working fluid. He said in this case the working fluid is steam. So in this case I will be using a steam table. If we have steam or water at 100 kilopascal, 4 times actually the atmospheric pressure and the temperature is equal to 200, I think this should be actually a superheated steam. But anyway, you have to check. So in this case we have pressure and temperature are given. So in this case I will be using this with this pressure to table A5, then I will get the saturation temperature. And to compare the saturation temperature with this given temperature, you will find this given temperature is greater than the saturation temperature. You can check this value. Then in this case, the state is superheated, and I will be using actually table A6 in this case. I need to calculate the boundary work, so I need a specific volume V1 and a specific volume V2. So from this table, we can get the value of the specific volume V1, and the state is superheated. Now, if the state is superheated, and at the same pressure, we added heat. So it will continue actually superheating. So in this case, the second state will also be actually superheated. If you want actually to do the check again, given pressure and temperature, you can just make it again. With this pressure, I will get the saturation temperature, compare it with the given temperature, you'll find the given temperature is greater than the saturation. So in this case, I will be using table A6 to calculate the specific volume V2 in this case. Okay, you can just get those values and substitute. Then we can calculate here the boundary work. Will equal to the pressure, which is equal to 400. We can keep it as 400 in kilopascal, so that the work can be calculated in kilojoule. Multiplied by mass, which is 5, multiplied by specific volume V2. You can check this value 0.592 minus 0.534. Then we can calculate actually the value of the boundary work. It will be in kilojoule 122 kilojoule. The work is positive in this case because we have expansion process. The piston will be, the gases or this steam will be expanding in this case. The volume is increasing. We can represent this process, Shabab, on the PV diagram. This is a constant pressure process with respect to the saturation curve. State number 1 was superheated. Under constant pressure, it will be just a horizontal line until actually second state actually is also superheated. So constant pressure line, it will be just a horizontal line on the PV diagram. So what about the TV diagram? This is the TV diagram, okay? And this is the saturation curve. On this saturation curve, this is actually the line of constant pressure, representing a constant pressure line. This is a line of constant pressure. State number 1 was just actually in the superheated zone. So this is state number 1, and we added heat, and state number 2 was also superheated. And this is the representation of the process on the TV diagram. TV diagram, this line is the line of constant pressure. And this is actually, this should be the representation of this process. Okay. Let's move to another example. The next example is a simple one. We have a piston cylinder device. It's for the isothermal process. We have developed this relation just so we can substitute in this example. So we have in this case also a gas and a piston cylinder device. So whenever you see a piston cylinder device, So that means, and we have the boundary, the piston is moving, then in this case we have to calculate the boundary work through integration of BdV. He said we have a piston cylinder device initially contains 0.4 meter cube of air. So piston cylinder device, so the system in this case is what? Is closed. We have to define the system either closed or open, so it is closed. And we have a gas in a piston cylinder device. Which kind of fluid? He said in this case air. So the working fluid is gas. So I will stick to the ideal gas equation of state BV is equal to RT, unless he asked me to use the modified equation BV is equal to ZRT. And we have a piston cylinder device, and this piston can move. Then in this case, we should have boundary work in this case, either expansion or compression in this case. So we have air. This air is initially has a volume V1 0.4 meter cube, and at a pressure V1 equal to 100 kilopascal. Okay, and temperature T1 is equal to 80 degrees Celsius. The air is now compressed, so we just compressed in this case. We just compressed this piston. Okay, so the volume will be reduced. He said the volume V2 is equal to 0.1 meter cube. This is the volume V2. In such a way, actually, this compression process is done in such a way, actually, to keep the temperature of the air inside the cylinder constant. So that means the temperature T2 is the same as T1 equal to 80 degrees Celsius. Okay, and we need to calculate actually the work done during this process. So which kind of work we have? We have boundary work, because we have movement of the boundary. We don't have electrical work, we don't have shaft work. And in this case, we have boundary work. Boundary work for isothermal process will just equal to V1 multiplied by ln V2 over V1. Or it will equal to, instead of V1, it will equal to MR T1. T1 is the same as T2, so it will equal to MRT. And R for air, I can get actually from table A1. If I can consider it as ideal gas, I can use this equation. Okay? Or we can just consider it, we have B1 and V1 directly. So in this case, it will equal to B1, which is equal to 100 kilopascal, multiplied by V1 0.4, ln V2, which is 0.1, divided by V1, which is 0.4 in this case. This pressure is in kilopascal, so this boundary work should be calculated in kilojoule in this case. We have compression, V1, V2 is 0.1 liter less than V1, so this term will be negative, and this case actually is work is a compression work, it will equal to minus 55.5 kilojoule. And this process, Shabab, is just a compression process. So the boundary work in this case is a negative. And this is the representation of the process on the PV diagram. We said this line represents the case of isothermal process. It is compression in this case, so this is state number 1, and this is the state number 2 in this case. Don't say where is the saturation curve. This is, we are talking about air, not steam. Air only in the gas phase. Steam can be liquid, can be saturated mixture, can be superheat. If it is steam, then we have to draw here the saturation curve. Okay, so inshallah we'll continue next time. And see also we can solve inshallah some more examples.